everyone, my name is Nitin. I am a software engineer at Facebook, and today I'm going to talk about holographic calling. To begin, let's take a look at this clip from Oculus Connect.
Will one day transform how we all engage with the world, making it feel more immediate, more intuitive, more natural, more human.
As you saw in this video, holographic calling experience can feel almost like an in-person experience. It's certainly more richer, authentic, and natural as compared to a 2D video calling experience. By holographic calling, I essentially mean 3D calling. It is best experienced in AR, but it can also be experienced in VR, on mobile phones, and on laptops. In this talk today, I'm not going to talk about a specific approach of building this product. However, I'll go over a broad overview of the high-level components involved and the technical challenges we need to overcome. Some specific challenges I'll talk about will be related to data compression, ABR, end-to-end delays, and bandwidth. Let's take a look at the ideal setup first. In the ideal setup, user will be surrounded by cameras and sensors. That means we will have 360 coverage of the user's body. This data can be processed on specialized hardware without any concern of compute and power. It will be sent over a really good internet with low delays and jitter. And on the receiver side as well, you will have specialized hardware where it can be processed, decompressed, and rendered on any device. A more practical setup will look something like this. User will have maybe 1 or 2 cameras and sensors in front of them, which means that we are not going to have full coverage. And we will need to fill in the gaps on the uncovered areas and reconstruct those parts so that we can create a full 360-degree 3D model. User will have a portable device, most likely, with limited compute and power, which means any compression or processing techniques that we use, they need to be compute and power friendly. This device will likely be connected to the public internet via wireless, which means that we will see the network having issues such as limited bandwidth, jitter, packet loss, and delays. And we need to do a good job in compressing the data and before we send it over the internet. Let's take a look at the high-level components first, both on the sender and receiver side. First, you have the capture setup, where each camera and each sensor is capturing the RGB texture and depth data for a specific angle. All of this data helps form a 3D point cloud. After that, the data will need to go to do some pre-processing there. We may need to reduce some noise, generate some segmentation masks, etc. Then the data will need to be compressed and sent over the internet using some real-time libraries such as WebRTC. On the receiver side, you will have a de-jitter buffer where the data will sit to take into account any jitter introduced by the internet or by the source. After that, it will be decompressed and a 3D mesh will be reconstructed. Then, based on the display, it will be rendered and shown to the user. In this slide, I'll talk about what are the data streams and what are the compression requirements. So one, you have for each camera and sensor, you are going to have the RGB texture and depth data captured, which will need to be sent compressed and sent over the internet. Then you will have some metadata such as segmentation mask, view information, etc. You will also have audio, maybe even spatial audio, and you need to synchronize the data and metadata. RGB compression is a relatively well-studied field. H.264, H.265, and VPX, they do a very good job of preserving video quality and reducing the bitrate. There's a good understanding of artifacts introduced by these codecs. Depth data, however, is a relatively less mature field in terms of compression. Let's take a look at what happens when you compress depth data using H.264. In this experiment, I took some samples for image and depth using Connect with the help of a colleague. In the first pass, I kept the data uncompressed, both for color and depth, and I ran them through our hologram pipeline. The result looked like this. Please ignore the background here. It's just a result of some segmentation went bad. But the core hologram quality here looks pretty decent. There are very few artifacts and very few black spots, as you can observe. Because it used the uncompressed data for depth and image, it served as the ground truth for my experiment. In the second pass, I kept the color image uncompressed, but I compressed the depth map using H.264. After I ran it through the same pipeline, the result looked like this. As you can see here, there are significantly more artifacts here. There are a lot of floating points in the space. The edges are not sharp, and there are a lot of black spots here and there. So this experiment informed us of two things. Depth is a lot more sensitive to quantization and compression as compared to RGB texture. With CRF2, it should have been virtually lossless, but still we saw so many artifacts. The second thing is the human visual system for texture are much better understood than depth. This can likely explain why H.264 did such a poor job at preserving the depth quality, whereas it does a good job at preserving the color quality. This is the landscape of codec, which can be used potentially for 3D data compression. I won't go into the details of each, but I want to highlight PCC. PCC stands for point cloud coding. It's meant to compress 3D data, which is exactly what we want. However, it's very new. It's being standardized right now as part of MPEG Immersive. The algorithms seem relatively less mature right now. There's no silicon support for it yet. There's no understanding of whether they can fit in terms of the compute and power envelope required for real-time calling, real-time transport, and on portable devices. In terms of ABR, 2D video ABR is straightforward. You start with a bandwidth estimate. You translate that to video bitrate by subtracting audio bitrate. From there, you determine the encoder parameters, resolution, FPS, bitrate. This is a well-studied space. You have models such as convex hull model, which can help you optimize the visual quality by picking up the right resolution. You have visual quality metrics available here, which can help you optimize the entire algorithm end to end. For 3D calling, however, it's more complex. You start with a bandwidth estimate here, but you need to translate it into video and depth bitrates for each of the views. From there, you need to determine the encoder parameters for RGB texture and for depth. So as you can see here, translating bandwidth estimate to bit rates for each of the individual streams, it's a joint optimization problem and it's not straightforward. It needs an understanding of relative importance of each of the streams on the final hologram quality. We don't have a model such as a convex hull model which can help us map bitrate to resolution for depth. We also don't have any well-defined quality metrics here which can be used. On the transport side, you will typically have a protocol built on top of UDP for unreliable transport. This will implement congestion avoidance, bandwidth estimation, loss recovery, etc., all designed to keep end-to-end latencies within real-time interaction bounds. A commonly used library here is WebRTC for good cross-plat support. In terms of quality of experience, you have three metrics here: latency, smoothness, and bandwidth utilization. You typically face a trade-off here where you cannot have most optimal performance in terms of all three, and you have to pick two of the three. One challenge is reducing end-to-end delays. End-to-end latency comprises of sender-side latency, network transmission delay, and receiver-side latency. Processing of 3D data incurs a non-trivial latency, which puts a lot of pressure on the rest of the pipeline in terms of having less latency budget to work with. The second problem unique to 3D calling is that it requires higher bit rates, which increase the air interface delays, queuing delays, and requires you to keep larger buffers. So the problem of end-to-end latency is not unique to 3D video calling, but because of these two problems, it becomes more challenging. At first, it may seem like nothing much can be done here, but we can push the envelope in a few areas. One, we can reduce the bitrate overshoots. We can deploy better bandwidth estimation, congestion detection, and encoder rate control algorithms to make sure that the outgoing bitrate always stays as close as possible to the estimated bandwidth. If we don't overshoot, that means we will not run into the risk of having self-inflicted delays. The second thing we can do is we can reduce and remove the need of having too many retransmissions. By deploying better loss recovery and error correction mechanisms, we can reduce the size of buffers needed on the receiver side and reduce the end-to-end latency. All of the examples mentioned here are pretty common in literature, but the adoption is low. For example, WebRTC still uses GCC and relies on retransmissions for error recovery. The second problem with transport is related to bandwidth. In this graph, you can see the typical behavior of WebRTC's bandwidth estimation algorithm. The green label shows you the available bandwidth, and the red label shows you the actual achieved bandwidth. As you can see, GCC leaves a lot of bandwidth on the table, and it does not do a very good job at bandwidth utilization. This problem is also not unique to 3D calling, but it's worse because 3D calling requires 2 to 3 times bit rates as compared to 2D calling. Having a good codec can help you by improving the compression efficiency and reducing the bitrate, but the bitrates are still higher than 2D calling, and they still scale as you add each view. We need to optimize the bandwidth estimation and the transport protocols to not only reduce delays but also achieve better bandwidth utilization. To sum up, I covered some of the challenges that we need to overcome to build a good holographic calling product. One challenge is related to 3D data and depth compression. Second challenge is related to ABR. Third challenge is needing metrics for objectively measuring visual quality. Um, WebRTC and similar libraries need to be optimized better for handling higher bit rates. And we need advancements in bandwidth estimation and error recovery. Thank you, everyone. Thank you for listening. Here is my email. Please reach out to me if you have any questions or you would like to discuss this further.